Today we're going to be talking about modeling and optimization. And here are the steps to modeling and optimization that I had written on the website above the videos. Make sure you have these written down in your notes. So first we want to draw a picture of the situation, and that's going to help you, especially if a picture isn't given. Then you write an equation that is to be maximized or minimized, and this is going to be in one variable. Make sure that you only have one variable in there. Find the domain restrictions. This is the one I sometimes forget. I'm going to work really hard throughout these lessons to make sure that I am showing you guys this. Then we take the derivative to find the max or min. We justify the answer by our first derivative or second derivative test. And then lastly, does your answer make sense? Okay, this first example is an example of a figure inscribed under a curve. So a rectangle has two lower corners on the x-axis, two upper corners on the curve y equals 6x squared. For all those rectangles, what are the dimensions of the one with the largest area? So draw a picture of what we have. That's our first step. So let's draw a picture. Okay, we know that graph is a parabola that opens down, that has y-intercepts of positive and negative 4, and then has a vertex at 0, 16. Your picture doesn't have to be super accurate, but gives you an idea. Now we have two lower corners on the x-axis. I don't know where they're going to be, but then two of them are up on our curve. And then I need to find the dimensions of the largest area. Now area is length times width. Let's figure out what our width is. So the width here from 0 over to this value would be x. So the whole width would be 2x, because I need this in one variable. Now our height would be our function value because it's a y number. So that would be 16 minus x squared. So multiplying that through, we get 32x minus 2x to the third. Okay, we've written our equation in one variable. We need to figure out our domain restrictions on x. Well, the largest that x can be is from negative 4 to 4. Because if I go larger than 4, your rectangle is going to be outside your curve, and that wouldn't make any sense. Now we take our derivative. So we find the derivative of area because I'm trying to maximize or minimize this. So that would be 32 minus 6x squared. Set that derivative equal to 0. Set your factor. Equal to 0. Solving for that, we get plus or minus 4 over root 3. Now I get the same thing because our rectangle is going to be symmetric. So I'm just going to worry about the positive version. And instead of using the first derivative test, I'm going to use the second derivative test, because the second derivative test actually is a lot more efficient in this case. So we find our second derivative, and our second derivative is negative 12x. I evaluate that second derivative at the critical points from our first derivative, which would be a negative number. So I don't really even care what it is. It's some negative number, which is less than 0. So if your second derivative is negative, evaluated at the critical points of our first derivative, then we know we have a max. We have a max by the second derivative test. Okay, make sure you're answering the question. For all such rectangles, what are the dimensions? Well, we know our x value is 4 over square root of 3. Actually, no, that's not our value. Our value is twice that. So our value is actually 8 root 3, okay, because it's twice as big. And now I plug in this 4 root 3 into the function. So to get my y coordinate out, and simplifying that out, we get a 32 over 3. So a 32 over 3. So these are our dimensions of our rectangle. Again, I had to multiply our x coordinate by 2 because our bottom base was twice as long.